So we're going to continue on and we're going to start talking about relations and functions so that we can find the domain and range. And we're going to talk about functions that are defined by graphs and equations. A relation is any set of ordered pairs. So everything falls in the category of a relation. We would write a set of relation as a set of ordered pairs. So I would use the set notation and I would use my x comma y, and there's my relation. A function is a relation, but with a special qualifier. Every distinct value of the first component of the order pairs, there is exactly one value of the second component. What does that look like? Let's look at A. So the first value is 0, -1, and -1. So this is no, because the same x value is paired with a different y value, so it's not going to be a function. And then in B, I have 5, 6, and 7 for the first, and there's no repeat of the x values. So yes, this is a function in the second one. So basically, we're looking at the x value does not repeat with a different y value in it. Relations can be defined a couple of different ways. They can be an ordered pair, like we just did. It could also be done with correspondence or mapping. It could be done in a table. It could be done in a graph, an equation, a rule. So there are different things here. When we're doing an equation, the x variable is always called the independent variable because that's what you plug in. The y variable is the dependent variable because it depends on whatever x is. So there's a lot of different ways we can show relations, and then we're going to use what we know about them to find domain and range. So for any relation that's defined by a set of ordered pairs, the domain are all the x values or the independent variables. The range is all the y values or the dependent variables. So here I have this table. Any table you're given, the first column is always considered independent or x. The second column is always considered dependent or y. So if I want to find the domain and range, the domain is the set of x's and the range is the set of y's. It's that simple. So you just really have to keep straight what side of the table that you're looking at. If I want to know if it's a function, I have all unique x values. So then yes, it's going to also be a function. Let's look at this on the graph. Now, our graph is a little bit trickier because I'm looking at the horizontal x-axis from left to right. So I'm looking at, if this has arrows, it's going to keep getting bigger forever. And same thing over here. So I'm going to have all real numbers from left to right. There's no way that the graph doesn't exist. So when we're doing the domain here, we're looking for where the graph does not exist. Now, if I want the range, I'm going to use bottom to top. And I can see that this little area up here has no graph, and it's never going to have a graph. So if I go bottom to top, that's negative infinity, and it stops at 4, and I'm going to use a bracket because there's no open circle. So left to right, bottom to top is how we're going to do this. Now, I want to identify functions that are defined by graphs and equations, and I'm going to have some other examples of domain and range, so you need to watch the other videos for that. It goes a little more in depth. A vertical line is how we tell if a graph is a function. If a vertical line touches the graph one time, then it's going to be a function. If it touches more than one time, then it's not going to be a function. And here are two examples that you can see right here. So if I use the vertical line test, no matter where I draw that vertical line, it's always going to touch one time. So you saw that animation? I'm drawing it all throughout the graph. It only touches once. So yes, it's going to be a function. A relation would be anytime it fails to pass that vertical line test. So I could force the relation to be a function by omitting values from my domain. I can also look at where in the graph would there be a double value. So a relation is going to have some certain guidelines in the domain. Values are not going to exist in the domain anywhere the fraction is equal to 0, the bottom of the fraction, because it's undefined. It's also going to be anytime I have a root of a negative number, that's going to be excluded from the domain as well. So if we're trying to find the domain with an equation and not a graph, these are the two situations we're looking for. We are going to play devil's advocate. We're going to try and find where the graph does not exist so that we can then exclude those values. So if I look at this, y equals negative 2x plus 7, and I want to know if it defines y as a function of x, and then give the domain. So first of all, this is the equation of a line. Any line is going to pass the vertical line test. So yes, it's going to be a function. Now for the domain, the only times the domain is not all real numbers is when the denominator of a fraction equals 0, or we have the square root and we have negative numbers. None of those can happen to this, so the domain is going to be all real numbers. Here, I have a square root. So right away, I already know I'm going to have an issue with the domain. So if I have a square root and I graph this using Desmos.com, it passes the vertical line test, so it's going to be a function. So that answer is yes. Now, to figure out where the negative values are in the square root, we're going to set it equal to 0. What's under there equal to 0. Or greater than or equal to 0. I'm going to get x is greater than or equal to 6/5. So my domain would be 6/5 to infinity. So you want to set what's inside equal to 0. And then when we're looking at the inequality sign, it has to be greater than 0. So some books will show you equal to, some books will show you greater than. If you do it greater than, it just helps you in that final step. So you just solve for x, and then your domain is greater than 6/5, which would be 6/5 to infinity. Here, I have y to the 4th equals x. Well, I don't know what that graph looks like. So I'm going to take the 4th root of both sides and graph y equals the 4th root of x in the Desmos.com or another graphing method. It does not pass the vertical line test when I do that. However, if I have the 4th root of x, I have a root there, so I have to look at where is x greater than or equal to 0, which because I get x is greater than or equal to 0, it would be 0 to infinity. Here, this is an inequality, but that's okay. It's a line. The denominator is never going to be 0. There's never going to be worrying about a negative under a radical. So this is a function because it's a line, and it's going to have all real numbers, so negative infinity to infinity. Here I have 6/5 plus 3x. Then oh wait, sorry, that's an inequality, so it's not a function. Sorry, there's a whole bunch of shaded areas. E, here I have my first fraction. So I would look at this in Desmos.com to figure out if it's a function. It is a function, the line only crosses once. Then to figure out the domain where it's excluded, I'm going to set the denominator equal to 0, and I get negative 5/3. When there's a fraction, you say negative infinity to where the fraction equals 0, union where the fraction equals 0 to infinity. That's always how you do it, because you're just excluding that one number, and that's how we show that one number is excluded in set notation. So there are different ways to think about a function, like the slide shown here. These are the 3 different ways we can think about it: as a distinct set of ordered pairs, or as a mapping or equation, or we can also think about every function is also a relation.